Hi guys, welcome to this quick recording concerning some questions that some of you guys have concerning some of the problems from chapter 38, part of the review obviously. So chapter 38, I have three problems actually, 30, 47 and 52. And from chapter 39 I also have three problems, 16, 17 and 52. And finally from chapter 40 I have these problems, 36, 37 and 43. So let me go quickly through these problems in here and the ideas behind them. Hopefully this review will be helpful. I know we did some of them in class, so some of you guys have questions. I know Octavio, David, and some other people might also have some questions, so I want to go through them. So I have chapter 38 in here, and the problems are, for problem 30, it says show that when an object moving with a 1/10 the speed of light, that the relativistic kinetic energy agrees with that of the classical mechanics within a 1%. Within a 1%. If it is 10% already. So basically, the kinetic energy in classical mechanics or in relativity is gamma minus 1 times mc squared. I'm sorry. And we're supposed to show that this is a within a 1% as long as the beta, which is the speed of the particle, is 0.10. So this kinetic energy within a 1% or 0.01 of the order of 1/2 of mv squared. So that's the classical, and this is the relativistic. Okay, so what you do in this case, the key thing is this: a factor of gamma minus 1 in terms of beta. Remember, gamma minus 1 is going to be equal to 1 over square root of 1 minus beta squared minus 1. So you use the Taylor expansion in here. This will become 1. The first order correction to the Taylor expansion is, of course, the first derivative of f with respect to x evaluated at x equals to 0 times x, except the x in here is beta squared, so you have to be careful in here. Okay, so you're taking the derivative with respect to the first time you're going to drop negative 1/2, and then you're going to drop a negative 1, and the first term is of course times x, because the value of that at x equals to 0 is 1, so it's x, and x is beta squared. And the next term is going to be of the order of beta squared, which is beta to the power 4. Okay, having said that, of course we're going to subtract to it, so this stuff is 1 plus that. We're just going to subtract 1, cancel the 1 from both sides. This term is exactly v squared over c squared. Cancel the c squared in here, and you will be left with 1/2 coming from the obviously the negative 1 and the negative 1 cancel. So we're going to be having 1/2 of mv squared plus correction of the order of beta squared. Remember, beta is of the order of beta is of the order of 1. Okay, so beta squared squared is going to be a very tiny correction, because the kinetic energy is going to be of the order of 0.01, and the first order correction is going to be of the order of 10 to the negative 2 squared. So it's going to be 10 to the negative 4. Obviously 10 to the negative 4 divided by 10 to the negative 2 is going to be a 10 to the negative 2, and that is 0.01. Okay, you're not comparing it to beta, you're comparing it to beta squared, which is the first correction in the which is the kinetic energy in classical mechanics. So that's problem 30. So it's of the order of 10%, the order of 1% if the velocity is within 10% of the speed of light. Okay. And next problem is problem 47. So problem 47 in here, it says an object disintegrated into two fragments. Basically, they give you the mass of the first piece, which is m1 equals to how much is it? 1 MeV per c squared, and they give us also its momentum, which is 1.75, so I'm going to call it p1. Its momentum 1 MeV per c, and particle 2, they give us its mass, which is 1.5 MeV per c squared, and its momentum p2 is 2.02 mega electron volts per c, per the speed of light. Okay, don't monkey around with these problems. Leave them as they are, the numbers as they are. If it's energy, it's going to come in MeV. if it's a momentum, it's going to come in mega electron volts per c. If it's a mass, it's going to be a mega electron volt per c squared. Don't change anything. As a matter of fact, for this entire problem, you could as well take c equal to 1. Okay? And everything is going to work the same. So the numbers 1, 1.75, 1.5 that is, and 2 are to stay intact. Don't multiply by 10 to the negative 6 or whatever, or 10 to the power 6 and divide by 1.6 and multiply by 300,000 meters per second. No, don't do that. Leave it as is, as the numbers they are, basically. And try to do this behavior for the entire part of this this class, basically modern physics. It's really, as a matter of fact, you could take also h equal to 1, the Planck's constant, or h bar equal to 1 for that matter. Anyway, so in here it asks for the mass and the speed of the original particle. Obviously, the initial particle had a mass m and it disintegrated into 2 pieces. So basically there is no more that particle. Its initial energy is somehow E of the particle, which was its mass, okay, rest mass squared plus its momentum must be equal to the energy of the outgoing particles, which is E1 and E2. And E1 is simply the same expression, except that everything is m1 c squared squared plus p1 squared c squared. Then m2 also, m2 also carries a different energy with it, which is its rest energy plus its momentum energy, okay, plus the energy coming from the fact that it's moving. Anyway, so these are in terms of the energies, so the energies must be the same. Furthermore, they tell us specifically that one of the particles, namely this one, went in the x direction and this one went in the y direction. So by conservation of momentum, so the first particle must have been coming, so if this went this way, the other one had the momentum that way. Granted, this momentum is slightly more than the other one, so this one is probably here. So in here, the initial momentum must have been in this direction. As a matter of fact, satisfies the Pythagorean theorem, but is because of the conservation of momentum. So P is the P of the first one in this direction, and the P of the second one in that direction using the Pythagorean theorem will give me the P of the outgoing particle. So this P is needed. So that P squared is equal to P1 squared plus P2 squared, and this is from the Pythagorean theorem. If it was any other direction, we really have to handle it correctly. Let's say, for example, P1 and P2 are making an angle other than 90 degrees, some weird angle, I don't care which one it is. So the incoming momentum is the geometrical sum of these two momentum. Of course, it's going to involve that angle somehow in the calculations. And basically, it's going to be P squared is going to be P1 squared plus P2 squared plus 2 times P1, P2 cosine of this angle between them. Okay, let's call it, I don't know, alpha, cosine of alpha. And this is simple geometry in here. Anyway, for this case, alpha is 90 degrees, so cosine of 90 degrees is 0, so that's why you have Pythagorean theorem at full fledged. Anyway, so you have P, you have the total energy coming from the sum of the two energies, because you have the m's of the outgoing particles, and you have the p's of the outgoing particles, so you have their total energies. Therefore, you have the total energy of the incoming particle. So what's your missing? Its mass. You can solve for its mass. Once you find its mass, you should be able to answer the second part, which is the speed of the particle, because now you know how much energy the particle has, which is again just that sum, E1 plus E2. You already did that, and that must be equal to gamma times mc squared, and you just computed its m. From this calculation you can find its m. Once you find its m, you can find gamma as being the ratio of the two energies of the two outgoing particles divided by its mass times c squared. So you really need to answer the mass of the incoming particle first, which is again just by adding these two energies, equating them to this quantity, where p squared is just given by the Pythagorean theorem. Once you do that, you find gamma. Once you find gamma, you can find how fast the particle is moving. Remember, gamma squared is equal to 1 over 1 minus beta squared. From here you solve for beta being equal to the square root of 1 minus 1 over gamma squared. So once you find gamma, you can find beta, and don't multiply it by the speed of light. I know you're going to find a fraction of the speed of light. Let's state it. The speed of the particle is 0 point something. The speed of light, 0 point, let's say for example 3 or 4 or 5, it doesn't matter. It's going to be a fractional number anyway, less than 1. So this is this problem 47. Okay. Problem 52. Problem 52 is actually similar in a sense. You have an iron 57 atom, and it disintegrates, not it emits actually a photon, and they gave you the energy of the photon to being 14 kilo electron volts. They also told you the rest mass of this M50 of the iron 57, so its mc squared is actually equal to 8.6 times 10 to the negative 9 joules. There is a problem from the get-go. The units don't match, so we really have to match the units. First of all, we're going to divide by the charge of the electron times 10 to the negative 19. That gives me 10 to the power 10 in here. Instead of joules, of course, it's going to be electron volts. And in order to convert it to a kilo electron volt, I'm going to divide by 1000, so it's going to be 10 to the power 7. 8.6 divided by 1.6 is some 5 point something, 5 and some change. Usually try to keep 2 decimal points because there is actually a sig figs in here. There are three sig figs, okay, for both the energy of the photon 14.0 kilo electron volts and that of the mc squared, which is 8.60. So there are 3 sig figs in here that you need to retain, times of course 10 to the power 7 kilo electron volts. Again, this is the energy of mc squared. This is the mass of the iron 57. What they want to know is actually its kinetic energy, the recoil motion of it. Obviously, I need the momentum of these particles. Since the photon has this much energy, its momentum is given by basically P is equal to energy of the photon divided by C, because again the photon has no mass. Okay. So this is its momentum, and this is actually the momentum of also, so this is the momentum of the photon, this is also the momentum of the recoiling iron 57, because remember iron 57 was here, it emitted the photon, it has this momentum. The other particle in here must recoil with the same momentum. By conservation of momentum, P plus P gamma must be equal to 0, because if you read carefully the problem, the iron nucleus itself was stationary, was at rest initially, so it did not have any momentum. So at the end the sum of the momenta is 0, which means in magnitude the two momenta are equal. Now you have P of the recoiling particle, so that total energy of the recoiling particle is mc squared plus P squared C squared must be subtracting from it the so this is, I'm looking at the kinetic energy, so this is the total energy minus the rest energy. Okay, the only caveat in here is that the numbers, this is 10 to the power 7 times some 5, okay, squared. This is 14 squared minus, under the square root of course, minus something times 10 to the power 7. Okay, I'm not, so for your case you really need to pick up the other 2 digits, otherwise this is not going to be a correct answer. Okay, anyway, if you do this numbers on a calculator, it's going to give you 0, but that's not the correct answer, because we know this is going to be something 25, probably 30, because there are some change in here that I didn't write. 10 to the power 14, and here 14 squared is what, 200. I know it's not exactly 200, but I'm getting an order of magnitude. 200 plus 10 to the power 14 is going to be practically 0. You subtract from it the same number, it's going to be, I mean not practically 0, it's going to be the same number actually. When you square root it, it's going to be the same number as the other one, is subtracted going to be 0. So don't do that. Instead use a Taylor again. So what you have in here, you have, take out the 5 times 10 to the power 7, 5 and some change. Of course you will be left with 114 over 5 times 10 to the power 7, the whole thing squared, and subtract from it 1 after you factor out that 5 point some change. Now if you do the Taylor series of 1 plus x under the square root minus x minus 1, this is going to be 1 plus x over 2 minus 1, so practically it's going to be x over 2. It's this number divided by 2 times that, so it's going to be the correct value for the kinetic energy is going to be 1/2 times 14 squared divided by 5 and some change times 10 to the power 7. okay? And it's going to be in kilo electron volt if I was careful enough when I did the corrections in there earlier. So it's going to be in kilo electron volts. Again, after you do reductions and everything else, the answer probably you need to change it, because this is 10 to the negative 7, okay? I know you're wondering what happened to the square. Well, the square is cancelled by that number because you expand, you're going to multiply by it, okay? So it's going to be something of the order of an electron volt. Remember, this is about 200 divided by 5 something, so it's going to be about some number 10 something times 10 to the power negative 4 kilo electron volt, which is some small number. So again, please carry on the calculations. I'm not really at this point, I'm just giving you the guidelines on how to do these problems, okay? So now I'll move on to problems from chapter 39. And those problems, I'm looking at them 16, 17, and 21. Those are the ones that have the questions. So let me do 16, 17 quickly, talk about them. 16, it gives you a photon. They gave you an X-ray actually. Its wavelength lambda is 120 picometers. And there goes a scattering. Find the scattering for this at different angles. Okay, so basically you want the outgoing lambda prime first. Lambda minus lambda prime is lambda c times 1 minus cosine theta. Okay, lambda c is 2.43 picometers. This is given to be 120 picometers, so lambda prime is going to be simply equal to 120 picometers. Everything is in picometers in this problem now, times 1 minus cosine theta. What theta gave you the values of, what is it, 30, 60, 90, 120, 150, 180, and increments of 30. So basically this is the angle, so it's going to be theta equals to, the only problem with this GeoGebra business is that it has to be converted to radians, because sometimes it doesn't work great in there. So the angles are 30, 60, 90, 120, 150, and 180. So this is the angle, and they want to find lambda prime, so I'm going to call it lambda prime just for the sake of calling it in here, lambda prime, using GeoGebra, of course. If you 120, everything is in picometers, plus 2.43 times 1 minus cosine, and here is where I need to be careful. This theta is not in radians, so I have to be careful with it and convert it to radians. So right now it's in degrees, so I have to multiply it by pi and divide by 180. 180. Okay, obviously this is the numbers that I have in here for my scattering. Okay, because for some reason I'm using too much of a precision in here, so let me go back into the precision in here, just pick up 3 decimal points. Okay, why 3? How about sig figs? 3 sig figs. Okay, so that's what I was supposed to do. No, 3 sig figs is not good enough, so because the last 2 values are not good. The last 2 values are actually getting me the same value in here. Okay, so that's better now. Okay, anyway, the highest energy should be for theta equals to 180 degrees, because you will have cosine of pi, and cosine of pi is negative 1 minus, so I have 1 minus minus 1, so that's going to be the highest incremental wavelength is that much. Okay, and we're supposed to find the maximum recoil energy of the photon. Remember, the energy of the photon really corresponds to the biggest change in wavelength. You start with this much wavelength, which was kind of short, and it lengthens to the maximum, and that occurs of course for theta equals to 180 degrees. And if you do the calculations, obviously I really need to calculate the energy, the kinetic energy the electron gets, and the kinetic energy the electron gets is going to be this is the kicked electron, is going to be hc over lambda, the initial energy, minus hc over lambda prime. Obviously I'm going to plug in the numbers in here and we can go through the calculations. Okay, the highest value of lambda will correspond to the least term of that, and that least term, of course, we're going to be the maximum energy is going to be imparted to that electron. Okay, so we have that. So now since you have lambda and lambda prime, you should be able to compute these values in here. Okay, so this is hc over 120. Everything is in nanometers, so make sure you convert everything to proper units, please. Divided by hc over 120 plus some change. Okay, so you're going to do the calculation. So you're going to find how many in here? 1, 2, 3, 4, 5, 6 values for lambda prime. You will find 6 values for the kinetic energy of the electron, and you will indeed detect that 180 degrees will correspond to the highest kinetic energy. For theta equals to 0, there will be no change in the momentum, because no change in the the electron doesn't get anything, so the photon just barely nicks the electron and goes by, so it's not going to really get anything out of it. So lambda and lambda prime are going to be equal, and that's expected because when theta is equal to 0, I have 1 minus cosine of 0, which is 1, and that's going to give me lambda prime equals to lambda. So there is no change in energy. This whole quantity will become 0, and the electron doesn't get any kinetic energy whatsoever. When lambda is equal to 100 and when the angle is 180 degrees, at that point the lambda prime will be its max value, and that is going to impart the maximum kinetic energy to the electron. Okay, and that is because again you will have 1 minus 1, and that is going to be 2, and that will correspond to the biggest shift in wavelength. This is basically the maximum momentum imparted to a particle when it recoils off of something. Okay, so that is this problem, and that's the explanation for it. Problem 17. Problem 17, it says that they gave you lambda, and for some reason they gave it to you in nanometers. So I'm going to take it in picometers, 1.6 times 10 to the 1.6 picometers already. Why do I have to bother with it in nanometers or anything else? For what photon scattering does the recoiling electron have kinetic energy equal to that of the scattered photon? This should be easy to solve. Okay. The initial energy is hc over lambda, so this is the incoming photon. Okay, the outgoing photon has an energy hc over lambda prime. That's the scattered photon. The electron has a kinetic energy, which is its kinetic energy. But in here, they said that it's equal to E prime, which is hc over E prime. By conservation of energy, hc over lambda must be equal to the kinetic energy of the electron plus that of the energy of the photon, hc over lambda prime. Why is it E prime? Okay, this and this are equal, so that means that 2 hc over lambda prime are equal to hc over lambda. Cancel the hc, that gives me that lambda prime is equal to twice lambda. That means that the energy was lost from the initial photon, and that energy basically resulted in a lengthening of the wavelength, lengthening of the wavelength. That means the frequency is getting less frequency, less energy, less frequency, a longer wavelength. Remember the dispersion law that connects frequency and wavelength. This dispersion law is useful always. So as the wavelength increases, the frequency goes down, because the speed of light is the speed of light. Okay, so we have that, but we didn't solve anything. They want to know the kinetic. What is the question? For what photon scattering angle? They want to know the angle theta that makes this whole thing possible. Remember, lambda prime minus lambda equals to lambda Compton times 1 minus cosine theta. The question is theta. Okay, so this is 2 lambda minus lambda equals to lambda c times 1 minus cosine theta. Okay, obviously this is lambda equals to lambda Compton 1 minus cosine theta. This is equal to 1.6 picometers. This is 2.43 picometers. There is no need to convert anything. Everything is in proper units. And from here you solve for theta. Okay? Just divide by 2.3 and move things around and use the arc cosine. Okay? So this is straightforward, hopefully. If you have any questions, please don't hesitate. Okay? I know the exam is on Wednesday and today is Monday, so hopefully you guys will be okay. Now problem 21 is a little bit of an involved problem. So problem 1, it says in the Compton scattering, an X-ray scatters through an angle of 17.4 degrees. So they gave us data in here, and from an electron that is initially at rest. So the photon had the electron had no energy and no kinetic energy in the beginning. The electron recoils with a speed of 2000. So they gave us V. Okay, when I was trying to do it with David the other day, we went to relativistic, and that is not good actually, because you can clearly see if you divide this by 300,000 kilometers per second, the speed of light in order to find beta. So beta is a very tiny number. As a matter of fact, 218,000 divided by 2,180 divided by 300,000 is a ridiculously small number. 2,180 divided by 300,000 is 0.07. And don't forget, we're supposed to square this at some point in order to get the kinetic energy and things like that. So this is really, how many zeros? Do I have enough zeros? Yes, you do. So when I square this quantity in here, even GeoGebra. So this is how much it is, ridiculously small number. So there is no need to go relativistic in the problem, stay classical. Okay. So the kinetic energy for the recoiling electron is simply equal to 1/2 its mass times its velocity squared. Okay. And the velocity is given, its mass is known. This is 9.11 times 10 to the negative 31 kilogram. That's the mass of the electron. Okay. So what else is asked in here? So we know that, but this is this energy, so we can compute. So this is a given number. Let's say, for example, it's 5 joules or 1 joule. It doesn't matter, okay? Just a number. So this must be the difference in energy that the photon lost when it's scattered. So there is a connection between lambda and lambda prime. We don't know what this lambda or lambda prime is. There is another relationship between lambda and lambda prime, and that is the Compton scattering law that we derived in class, and we have data. So we have two equations with two unknowns. The equation 1, where we don't know lambda, lambda prime. Equation 2, where we don't know lambda, lambda prime. So technically we can solve for them and find lambda, because we're asked what is lambda. Once we find lambda, we need lambda prime, and I will tell you why. Because the next part of the problem is asking for the direction in which the photon has scattered. Okay. So the electron was sitting in here minding its own business. It was not moving. The initial photon comes in one direction, so this is gamma. That photon is scattered at an angle of 17.4 degrees. So this is gamma prime. This angle is 17.4 degrees. Now the electron is kicked in one direction by let's call it phi. Okay, its momentum is just mv. We're using classical. Remember, I just made the case for it that you don't need to go relativistic in this problem. So the momentum is P equal to mv, the mass of the electron, the speed is given. Don't forget to convert it into meters though. 2000 times 10 to the power 3 meters per second, otherwise you'll get some nonsense numbers. Okay. And this momentum in here is equal to the energy over c. Okay, which is h over lambda prime. So you need the lambda prime. That's why I said we need to compute it to find the momentum of the outgoing photon p prime. So you have p, you have p prime. The momentum is conserved from before equals to the momentum after. Forget about the components in the x direction, in the direction of the initial photon. Let's focus on the direction perpendicular to it. This component of this momentum, which is mv times an angle which we're supposed to find, sine phi, must be equal to this momentum h over lambda prime times the opposite to the angle 17.4, sine of 17.4 degrees. Equate the two, you have everything. You have lambda prime, which you computed from the first step. H is known, the mass of the electron is known, the velocity is given, the angle of the outgoing scattered photon is given. The only thing that is not known is phi. Once you find this relationship, the arc of sine of this over that, and you're going to get the angle phi, the direction in which the photon has scattered. Okay. The other problem in this stage in here is, so no, we're done with 39. So let's move on to 40. For 40, if I can find them. Okay, and it starts at 36. So 36, it gave you a marble rolls in one direction. So basically a marble rolls with a speed, so they give us the speed of the marble 0.8 meter per second. Obviously if I plug and divide this by 300,000, it's going to be impossible to use classical mechanics. I mean to use relativity, I'm sorry. So the kinetic energy of this marble, it's 1/2 mass times velocity squared. Since they asked us to do an order of magnitude, I'm going to take an order of magnitude for the mass of the marble. Marbles are usually not 1 gram, neither 1 kilogram, unless you're doing a bowling ball. So in this case, we're going to take it about 100 grams. So the mass is 0.1, the velocity is given, so I'm going to take 1/2 times an order of magnitude, which is 10 to the negative 1 kilogram, that is 100 grams, times the velocity squared, which is 0.8 squared, and that's 0.64 divided by 2, that's 0.32 times 1/10, so it's 0.032 joules. Okay, now they said an order of magnitude, it's inside the shoebox. Shoebox is not a meter high and it's not a centimeter high, so I'm going to say about 10 centimeters high. Again, the height of the shoebox is 10 centimeters or 0.1 meters. And then the width of it, I'm going to take it about 1 millimeter, 10 to the negative 3 meters. Okay, so I'm going to estimate it. It's not 1 centimeter, by the way. Probably maybe 1 centimeter, maybe 10 to the negative 2. But that's going to make it worse. Okay, so if you want to put 10 to the negative 2, it's going to make the probability for it to tunnel outside of the shoebox is going to be worse. So if you make it thinner, there is a potential that it could make it. Anyway, I need my beta, which is square root of 2m times the difference in energies divided by each bar. Okay, the difference in energies, I need mgh, by the way. The potential energy is in this case due to gravity, so it's the mass is 0.1, g is 10, h, I said it's 10 centimeters, is about 1.1. Okay, 0.1 and 1, that's 1, so it's about 0.1 joules. That's the problem. It does not have enough energy to have 0.032 energy, so it cannot escape this shoebox, at least classically. In quantum mechanics, there is a probability for it to do so, and the probability is proportional to, it's proportional, not exactly, there is another factor in here that I'm not writing, of e to the power of negative 2 beta times L. Well, we have beta, so let's compute beta in here. Beta is going to be square root of 2 times the mass times the difference in energies, which is 0.1 minus 0.03, 0.1 minus 0.032. I'm going to approximate it to 0.07. Okay, I don't care about the change, it's 0.68. So it's 0.07 times, so that's the difference in energies divided by each bar. Each bar is 1.05 times 10 to the negative 34, but I'm not going to write that. I'm going to write just 10 to the negative 34. Again, we're doing an order of magnitude. We're not doing exact calculations in here, so we're not really after precision in here. I mean, what I'm saying in here is that you're going to get a tiny number. That's the bottom line. So, how much is beta in here? Square root of 0.07, so 0.007, when you multiply it by 2 is 0.14. When you square root 0.4, it's going to be around 0.1. So this is about 10 to the negative 1 times 10 to the power 34 when you take it upstairs. Remember, 10 to the negative 34. Again, all that matters are the powers, 10 to the power 33. So beta is huge, okay, which makes t extremely small, because t would be then e to the negative 2 times 10 to the power 33 times the width, which we said 10 to the negative 3. We could have made it 10 to the negative 2, but that's going to make this number actually bigger than what I'm chosen here. So it's going to be e to the negative 2 times 10 to the power of 30. Okay. Anyway, so I know e cubed is roughly 10 because e is about 2.71, and I could borrow one of the 10s from the 10 to the power 30 and make it roughly 10 to the power and make it roughly 3 by 3, and use that e cubed to be part of the solution. So it's going to be about 10 to the negative 2, because I still have a 2 in there, times 3, one of the other 3's is left, times 10 to the power 29. 2 times 3 is about 6, which is about 10. Again, we're doing an order of magnitude. 10 to the power 1 times 10 to the... So it's going to be back to 10 to the negative 30. It is a huge number. I mean, the numerator, the exponent, that is, to the negative of that power. So it's practically 0. So it's impossible for it to escape the shoebox classically. Okay, that's basically what this problem is. Problem 37. An electron confined to a box, absorbs a photon. I'm still in that shoebox from the previous problem, with the wavelength lambda, and as a result the electron makes a transition from the n equals to 1 to the n equals to find the length of the box. Okay, so the photon, the electron absorbed a photon and jumped from n equals to 1 all the way to n equals to 3 level, passing by n equals to 2. So it jumped this way. Okay, so it gained energy, and that energy is given by hc over lambda. HF, which is hc over lambda. That must be equal to, remember we did this in class and we found basically that the energy levels for one-dimensional, you have to be careful in here, and the one-dimensional box is given by this quantity. So this is En squared. This is En. So in other words, in here the energy is equal to exactly h squared over, what is it, 8 ml, where m is the mass of that electron, times 1 squared, and in here it's going to be equal to h squared divided by 8 ml squared times 3 squared, which is 9. So at the end of the day, the energy would be enough just to transition from 1 to 3, and that energy is going to be h squared over 8 ml squared times 9 minus 1. 3 squared minus 1 squared, which is 9 minus 1. 9 minus 1 is 8, and 8 cancels, so this is going to be equal to h squared over ml squared, and that gives me an equation where you can find the length of this box, the length of the box where the electron is contained. So it's going to be equal to what? L. It's going to cancel one of the h's basically. So it's going to be h in the numerator divided by the mass and the speed of light in the denominator. Do I have anything in here other than the speed of light? Yeah, there is an hc. Kind of curious in here because this is... Am I missing something in the numerator? Okay, let's check it. H is in joule second. M is in kilogram. Meter per second. Okay. Joule is kilogram meter squared per second squared. Oh, I'm missing the lambda. Okay, so I'm missing a meter in here. We have to multiply by lambda in here. Okay, so that makes more sense now. I'm happy, I think. Let's see, make sure it works. Okay, and times second, of course, from the action, because there is an s in here. So this is joule times second times meter divided by kilogram meter per second. One of the seconds cancel this one, the other second cancel that, the meter cancel the meter, the kilogram cancel the kilogram, and we have meter squared and the square root, which is meter, and all makes sense. Okay, so this is the value of the length of the box, and then they ask find the length of the box, and then what is the wavelength lambda prime of the photon emitted when the electron makes a transition from n equals to 3 down to n equals to 2. So the electron now transition back. Remember, this energy is less than this energy. As a matter of fact, we can find the transition. That's how much photon is going to be emitted, hc over lambda prime, when it goes from h squared over 8 ml squared of from 3 squared minus 2 squared. This is 9, this is 4, and the difference is 5. Okay, so this is how much energy, and we need to compute for that to find the correct value of hc over lambda prime. Obviously, we could do the whole math in here and spend, so it's 5 over 8 times h squared divided by ml squared. If you notice from this relationship, h squared over ml squared, that's exactly hc over lambda. Okay, hc over lambda cancel the HC over the HC, and lambda prime should be equal to 8 over 5 lambda. And that makes sense because it's less energy, longer wavelength. Remember that dispersion law? I wrote it somewhere in here when I was talking about it. I forgot. Anyway, lambda f equals to c. That means the higher the frequency, the shorter their wavelength, or the less the frequency, the less the energy, the longer the wavelength. Okay, and it's true in this case too. So the emitted wavelength is going to be 8/5 of the initial wavelength that came in and made the whole transition happen. Okay. Finally, problem 43. Problem 43, it gave you a wave function that is defined as, actually it's a piecewise function, square root of 2 over a exponential of negative x over a, and for x positive, and for x negative, they said that it's 0. Okay, they are saying in here, find this scatter probability density. Well, the probability density is just the square of this function. So it's psi squared in this case. Remember, this is 1D, so the element of volume in this case is just dx, so you're not going to add another 4 pi over r squared or anything like that. So it's going to be equal to 2 over a exponential of negative 2x over a. Okay, and if we plot this function, obviously it's 0 for less than, so this is at x positive. For x negative, you're going to square 0, so you're going to get 0. And then it picks as a certain value at x equals to 0. This is 2 over a, and then it drops exponentially. Okay, so this is how you sketch it. And it says find the probability of the particle. Find the probability of the particle when x is less. So it's 0 because there is no probability in here. The probability density is 0, therefore the probability of the particle being from negative infinity to 0 is 0, because you're going to integrate 0 from negative infinity to 0, and you're going to get 0 because this is a bounded integral. So don't be tempted by that constant in the integration. C, show that psi is normalized. So psi is normalized if and only if the integral of psi squared from negative infinity to positive infinity is 1. So, and let's check that. We're not saying it is equal to 1, but we're saying it should be 1. So if again, this quantity is going to be 2 over a exponential of negative 2x over a, the integral from negative infinity to positive, from 0 to infinity, because from negative infinity to 0 it's 0. So this should be divided into 2 regions, where part of it is 0 and the other part is this quantity. This is from 0 to infinity. Okay, so in here we're going to do a variable change. So we're going to go for y equals to 2x over a, which means that dy is equal to 2dx over a. And this is 2dx over a, and that is x over a. So this integral becomes from 0 to infinity, because the boundaries of integrations do not change. When x goes to 0, y is 0. When x goes to infinity, y goes to infinity, of basically exponential of negative y dy. And this is simply equals to negative exponential of negative y between 0 infinity and infinity. At infinity, this integral vanishes, and at 0 it's equal to negative 1. I'm sorry, negative 1. So it's going to be 1 minus minus 1, so it's going to be 1. Indeed, it is. Yes. Okay, so it is. It checks as being equal to 1, so it's normalized. And then find the probability of the particle between 0 and a. Between 0 and a, you're going to do the same thing, except the boundaries of integration. So the probability between a and 0 and a, I'm not saying minus, okay, 0 and a, is equal to the integral again from 0 to a only of 2 over a exponential of negative 2x over a dx. Again, we're making sure that x, we're going to make that same change of variable, except now the boundaries of integration for x equals to 0 is 0, but for x equals to a, y goes to, what did I call x? Yeah, 2x over a. So when x equals to a, y is equal to 2. So the integration changes from 0 to 2. Exponential of negative y dy, okay, where y is the same change of variable as before, 2x over a. Okay, So now it's just a matter of doing this integral, which is again similar to before, except the boundaries of integration change. So this is going to be equal to with a negative sign, exponential of -2 minus minus 1, which is plus 1, or 1 minus 1 over e squared. Okay, if you plug in the number in calculator to get how much this thing is, so it's going to be 1 minus 1 over e squared. I mean, sometimes the calculator don't have e, so it probably are better to write it as 1 minus 1 over 2.71. So it's worth remembering the value of e squared. It's 86%, okay? So 0.86 or 0 or 86%. So this probability for the particle to being between 0 and a, let's say this is a, is 86%, which means less than 14% is outside of this region. Okay, obviously it's 0% in here. Okay, so that is basically the probability of finding the particle anywhere outside between 0 and a, which is 86%. This number is 0.86, and some changed, so I'm writing it as 86%. Okay, always a probability, no matter what, at best is going to be equal to 1, and that is for sure, you know, the particle is somewhere. Okay, again, hopefully this will be helpful. If not, please reach out. Thank you.